so this is our first lesson video for AP Chemistry. So we're going to start with Chapter 1, and this video is going to cover Section 1.1 through 1.4. So if you have me for class, you will quickly find that I'm not covering any of this in class. And why is that? Because you should already know all of this from Honors Chemistry. Okay, so this whole chapter I will not be covering in class. I'm just making the videos to make sure you know what's going on beforehand. So, the study of chemistry. Chemistry is the study of matter, its properties, and the changes that matter undergoes. Again, you should have already gotten a taste of that in Honors Chemistry. Matter is anything that has mass and occupies space, and atoms are the building blocks of matter. Elements are made of only one type of atom, and molecules are two or more atoms that are joined together by bonds. So remember, molecules can be two or more atoms of the same element, like O2, or it could be two or more atoms of different elements, like HCl. And it doesn't have to only be two atoms. Those were just the examples I just said. So that was Section 1. Woo, breezing through this. Section 2, classification of matter. So, the states of matter, we have a gas that has no fixed shape or volume and can easily be compressed. Whoop, that should say be. The particles are far apart. So, for example, O2 gas. A vapor is the gaseous state of matter of a substance that is normally a solid or liquid at room temperature. Example, water vapor. So, the only difference between a gas and a vapor, they are both the gas state, is a gas at the room temperature, whereas a vapor is a solid or liquid at room temperature, like water, and we need to heat it to become a gas. That's when we refer to it as a vapor. So that's why you don't hear anybody say water gas. Everybody says water vapor. Then a liquid has an indefinite shape but a definite volume. The particles are incredibly close together, but they can flow past one another. Okay, so liquids, the particles are still incredibly close, just like a solid. The only difference is a solid, the particles are orderly and in fixed locations, whereas in a liquid, they're random and they can flow past one another, but they are still very close. And then a solid has a definite shape and volume. The particles are close together and orderly since they only vibrate in their fixed locations. So yes, they are moving, but they can't move past one another. They can't switch places. So a pure substance has a constant composition. Pure substances can be elements or compounds. An element is made of one type of atom. Elements can be composed of atoms or molecules. So for example, nitrogen is an element. It's just made of nitrogen atoms. But because it's one of those 7 diatomics, it's N2, it exists as molecules of N2 and N2. Oxygen's the same way, it exists as O2. But not all elements exist as diatomics. And then a compound is composed of 2 or more elements bonded together in a fixed proportion. So for example, carbon dioxide is a compound. It's carbon and 2 oxygens bonded together. So it's made of a molecule, but it has more than one type of element. And then compounds can be broken down into elements by chemical processes. So you can break down carbon dioxide into carbon and oxygen, but you can't break an element down anymore through physical or chemical processes. So mixtures. A mixture has a variable composition. So homogeneous mixtures are variable but appear uniform throughout. So they're not actually uniform, it's just the particles are so small you can't see the difference. They are also called solutions, and an example is Windex. So Windex looks like it's pure, like it looks like it's just a pure blue liquid. But in reality, there's lots of different things mixed together. There's a base, usually like potassium hydroxide or sodium hydroxide. There's water. There's the dye to make it a certain color. There's usually some sort of scent that's been added to it to make it smell good. So there's lots of different things. We just can't see the difference. Heterogeneous mixtures have a variable composition in which the different parts are noticeable. An example is Italian salad dressing. So Italian salad dressing, I can see when those layers separate. I can see there's little pieces of garlic and different spices in it. I can see the different parts of Italian salad dressing. Mixtures can be made of solids, liquids, or gases, so it can be any of them. So here's just a chart to help you remember. So matter can either be a pure substance. If it's a pure substance, it has two options, element or compound. If it's an element, all the atoms must be the same element. So like if this was sodium, all of these atoms must be sodium. Or it could be a compound. So like for example, this could be CO2, carbon dioxide, like we just talked about. So we have one carbon, two oxygens. But notice every particle is identical. Each of the molecules is identical. So that's what still makes it pure. On the other hand, if it's not a pure substance, it can be a mixture. If it's a mixture, there's two options. You have homogeneous, heterogeneous. So remember how I just told you, homogeneous appears the same throughout, but you can see if we could zoom in on the particles themselves, they clearly aren't the same. But from, us just looking at it in reality, it's going to look the same throughout. All right, but this is a homogeneous mixture. Heterogeneous, you can see it's kind of layered. So here we have one type of particle, and here we have another. So if we were looking at this, we would be able to see the difference. Like think about oil and water, how it separates into layers. That would be an example of heterogeneous. So the first sample exercise, it says white gold contains gold and a white metal such as palladium. Two samples of white gold differ in the relative amounts of gold and palladium they contain. Both samples are uniform in composition throughout. Use the chart to classify white gold. All right, so it says, is it uniform throughout? So it says right here, both samples are uniform. So I'm going to say yes. So I go over here, homogeneous. It says, does it have a variable composition? Well, if you look over here, it says two samples of white gold differ in the relative amounts of gold and palladium. So yes, it does have a variable composition. So what is it? It is a homogeneous mixture. So that's what we would put for this one. Now, hopefully you should be able to easily do this question without this chart. Like if you struggled with the chart, or if you needed the chart at all, that is a huge red flag for this class, just saying. Okay, hopefully you could have just read the statement and immediately figured out, okay, well obviously it's a mixture. They told me it's a white metal such as palladium and gold, and then you should know what white gold looks like, and you can't see the differences, so that should have immediately made you think homogeneous mixture. Alright, so it says, which of the following is the correct description of the inside of a grapefruit? So it says it is a pure compound. Okay, hopefully that one was not even coming up into your mind. It consists of a homogeneous mixture of compounds. Well, when I cut open a grapefruit, the inside doesn't all look identical, so I would not go with homogeneous mixture. It says it consists of a heterogeneous mixture of compounds. Okay, I'm going to hold on to C. It consists of a heterogeneous mixture of elements and compounds, or it consists of a single compound in different states. Okay, well, grapefruit itself is not a compound, so we don't need that one at all. Alright, so really hopefully you could have at least narrowed it down to C and D, because it is a heterogeneous mixture, of course, because when you cut open a grapefruit, you can see different parts. Like there's going to be, like think about when you cut open an orange. The whole thing doesn't look the same. You have all the little segmented areas and things like that. So it would be a heterogeneous mixture of compounds. Okay, there's not elements that are just floating around in a grapefruit. Alright, so practice exercise number 2. It says aspirin is composed of 60% carbon, 4.5% hydrogen, and 35.5% oxygen by mass, regardless of its source. Use the chart to classify aspirin. So again, y'all, hopefully you don't need the chart at all, and you should be able to easily figure out what it is, but we'll go through the chart just in case. Alright, so it says, is it uniform throughout? Well, notice it has these percentages regardless of its source. So yes, it is. So then it says, does it have a variable composition? Well, again, it has these percentages regardless of where it comes from. So it is not a variable composition. So then it says, can it be separated into simpler substances? Well, here it tells me it's made of carbon, hydrogen, and oxygen. So through chemical processes, I should be able to break it down into the carbon, hydrogen, and oxygen. So can it be separated into simpler substances? The answer is yes. And so you should have gotten to compound. But again, you should have been able to do this without this chart. So once you know it's more than one element, you know it's not an element. And then once you know, regardless of its source, it has the same breakdown, that should make you know, oh, it's a compound. Okay, so please know you should not need this chart to answer these. All right, so section 1.3, physical properties of matter. Physical properties can be observed without changing the composition of a substance. For example, melting point. I can melt something and I'm not turning it into something else. Remember, a phase change is not turning it into a different composition. Chemical properties describe a way a substance may react or change composition. For example, flammability. So if I wanted to determine if something was flammable or not, I would actually need to set it on fire, which would change the composition. Intensive properties do not depend on the amount of substance, only the type of substance. So for example, density. So different substances have different densities, but it doesn't matter how much of a substance I have, it's going to have the same density as long as we don't change the temperature. And then extensive properties depend on the amount of the sample. So for example, mass. So like if I have a cup of water and a jug of water, they're not going to have the same mass even though they both contain water because they don't have the same amount. However, if they're both just water, they would have the same density because intensive doesn't depend on how much you have. So a physical change occurs when properties of a substance change, but the composition remains the same. Example, boiling water. So again, I know that some of you want to say, oh, well, when water's boiling, it's turning into steam, that's something different. That's not anything different. That's just water turning into a different state of matter. Okay, and a different state of matter is not a change in composition. And then a chemical change occurs when the composition of a substance changes. For example, burning wood. So when you burn wood, it actually turns into something else, changes composition. So distillation separates mixtures based on their different boiling points. And so distillation, we talked about this in honors chem, so I'm not going to harp on it. That's why you'll notice I'm going quickly through everything, because you should already know all of this stuff. Okay, so that's where if we have a mixture and we heat it, the substance with the lower boiling point will boil first, and as long as you don't allow it to keep heating to a higher temperature, once it stops dripping, you have separated your mixture. Filtration separates mixtures based on particle size. And then chromatography, which we did when we did the marker, the little quick lab at the very beginning of the year, where we did the marker and separated the colors of ink. Chromatography separates mixtures based on the differing abilities of substances to adhere to a surface. So, section 1.4, the nature of energy. Energy is the capacity to do work or transfer heat. Work is the energy transferred when a force exerted on an object causes the object to move in the same direction as the force. Force is a push or pull on an object. Heat is the energy used to cause the temperature of an object to increase. So as you can imagine, in chemistry, more than not, we're going to focus on the heat transfer. However, reactions can do work, and we'll talk about that later when we get more into thermochemistry. So, kinetic and potential energy. Kinetic energy is the energy of motion. It depends on mass and velocity. Atoms and molecules have kinetic energy, which increases as a substance is heated. So we know that when we heat a substance, the particles move faster. Well, kinetic energy is based on velocity or speed of particles. Potential energy is stored energy due to a position of an object. And then electrostatic potential energy arises from the interaction of charged particles. So as you can imagine, because in chemistry, when we talk about protons and electrons all the time, we will focus a lot on electrostatic potential energy. And then, super important statement. This is probably the most important statement in this entire video and something you should already know. Opposite charges attract and like charges repel. Literally half the stuff we talk about in this class, I mean maybe not half, but still, many of them are based on this statement right here. Okay, so we're going to end there for video 1. Hopefully you're finding all of this super easy and it's just a little bit of a review for you.